This is lecture number 37 E524 Digital MOS LSI Circuits, and today is November 17, 2020. So previously we have studied some sort of tunneling, where we have studied direct tunneling and also the Fowler nodine tunneling, right? Commonly known as FN tunneling. Okay, so let's follow that, and we also understand that with respect to given gate voltage at the floating gate device, you might have three different region. So this is the current this is the time when there is actually you are doing the retention, and here when it's a FN tunneling is happening with quite a high voltage than available VDD, then FN tunneling will happen, and you can program the device. Definitely, like in between there is a direct tunneling where Vox is lesser than VB, and here Vox is more than VB, right? Note that this voltage which you are applying at the gate, it's much higher than the required voltage of VDD. So if you are working at 180 nanometer, its typical voltage is 1.8, or okay, let's talk about 130 nanometer, which you are aware of. So 130 nanometer where you are using VDD of 1.2 volt, but when you are having, let's say, floating gate device at the gate, you are going to give more voltage than 1.2 volt, which is going to achieve such a condition, and you can program it, right? Okay, so in that case, yeah, other than that, we also understood that because of capacitance, the floating gate voltage is equal to GCR times VG plus QFG divided by CT. And this is the main governing equation. Now let's start with the operation, how it's working. Okay, I'm not writing anything here so that it's applicable to both of that. So this is a floating gate and this is control gate, and these are the oxides, and this is known as IPD, interpoly dielectric, or this is another one, right? So in this case, let's assume that we are applying here more voltage, and at the time source, drain, body are connected to 0 volt, right? So Vs is 0, Vd is 0, and V body is also equal to 0. And if I am applying here a pretty high voltage, let's say 15 volt, what is going to happen over here? So in that case, you remember we had following things. When you don't apply anything, this is floating gate, this is control gate, and silicon does not bend as we wanted. So when you are going to apply a gate voltage of 15 volt, application of 15 volt will take this one as down, and of course this will also go down. When you are doing this at the time, something like this will happen. And this is high enough so that it creates polar neodymium tunneling, so that FN tunneling will make sure that this is VB and this is Vox. So Vox is more than VB, and it allows to have the trapping of the tracking of the electrons. So when you are doing this, what is happening actually? Okay. So when it's a 15 volt, you know that at the floating gate with the consideration of 0.5 volt, 0.6 of GCR, this is going to be equal to 9 volt, right? So if it is 9 volt at this point, when time t equal to 0, at that time you can see that VFG is nothing but GCR times VG plus UFG divided by CT. So at the beginning there is no charge was available here, so this was already 0, and at time t equal to 0 this is becoming GCR times VG. However, as time is progressing, right, so what is going to happen in that case? By the way, you can see here when this is happening, so the in current, let's call it in current density, and the current which is getting out from here, the out current density, if we plot that at time t equal to 0, so Jn is here and J out is almost here. As we are, so this is time t equal to 0, and this is current density with respect to the time. But when you are going at time t equal to 1, t1, what is going to happen? Because of this, like earlier it was, if you look at this equation, now it's not time t equal to 0 anymore, and at time t equal to t1, this QFG will trap some charges over there, and some electrons might be there, so it will increase this voltage, right? And because of that, VFG is actually going in a different direction, right? Because FG is there. So by the way, these are the electrons, so the whole terms will get reduced, right? So this will be not plus, but it will become minus because of the electrons and all, right? So this term is relatively minus, or you can say that VFG, if you look at this diagram, that VFG will go up, because now it's not 9 volt, but it's going up 8 volt, 7 volt, depending on the time, right? As you are moving it, as it is going up, you know that you are going to be like going to change the tunneling. Instead of having such things, what is going to happen? You will see that at one point of time, still tunneling is there, but its approximation is trapezoidal, and it's going to be direct tunneling, right? So if you look at this current and all, the current which is going this side, because of this barrier in direct tunneling, has a lower current, but so this G in is started going down and G out is started going up, and there is a one point where both will be equal. It's known as the T set. So this time T set, this is going to happen. If you look at the charge, which is integration from 0 to T set, you can see that J in minus J out with respect to time is going to give you this value, and when you are going to draw this, you will see that this something like this. right? So this is QFG. Okay, so once this is like keep on increasing the electrons and it's going to be trapped. One point of time it's like there are no more electrons can go inside, right? So it will stop. At that time, like you can remove this, as we know that this is NVM flash memory, which has a characteristic that the power off is there. Still you can read and you can read the data, right? So here in this case, if you remember the time when we have started, so where is it? Yeah, so when we have started, we have understand two things very well, that when this place is empty, it's acting as a low VT, and when this place is filled up, it's a high VT, right? So in that case, let's assume that I already programmed this with, if I program this with some electrons, right? And there is a gate. Gate is not connected anywhere, but note that when you program it, you gave very big value, like something like 15 volt. You can give more also, or depending on the technology, you will give some value, let's say 15 volt to program. However, when you want to read it, you can read it not with the 15 volt, because again it will start working with the FN tunneling and all these things will be happening. So what we are going to do, we are going to apply here, let's say 1.8 volt, which is for 180 nanometer. The typical value of VDD is 1.8 volt, so we are going to use that 1.8 volt over here. So if it is 1.8 volt, in that case, what is going to happen, that these charges will not be lost, but if you understand that, okay, so this floating gate, this particular terminal, we are going to call it as a current sense, right? So if you're applying the voltages so that the current flow from here to here, and if you can read here, then it's 1. But because of this electric field which is available vertically, what is going to happen, it will hinder this, and there is like nothing will be read over here, so it will read as logic 0. However, in the absence of these electrons, actually because of this 1.8 volt, there is a channel, and because of that, source to drain, the current might be there, and you can read some current over here, and later on you can use, of course, the sense amplifier and other things, so that you can read the voltage that is going to be read as logic 1, right? So here when you are going to program it, you need such a high voltage which is going to make sure that this is going to happen, right? And yeah, yeah, tell me. So band bending diagram, when you are applying higher voltage, it goes down, right? So when it becoming, if you look at this, okay, I'll write this equation over here, that VFG is nothing but GCR times VG plus UFG divided by CT. So as this is increasing, but this is in with the minus sign, this overall VFG is going to be reducing, right? With the time. And the gate voltage it's at 15 volt. You don't change it. Look, these trap charges does not happen in 0 seconds. When you are writing it, it takes some time to get it trapped. If that voltage is rising, it will remain at 15 volts. No, then it's CC by CT only, right? This GCR is nothing but CC divided by CT. Because the parasitic capacitance, it does not change, right? So because of this increment in QFG, but in negative sign, this VFG is getting reduced. If it is reducing, so in band bending diagram, it goes up. As it's going up, so this will also go up, right? Earlier it was like this, right? When it was down, as it's going up, this will also change. So barrier will be there, and because of this direct tunneling, you cannot program it anymore. It's so while reading logic in 0 and 1, it depends whether the charges are there or not in that floating gate. And that's how, like, when you remove this, like if there is no power, still, like after 20 years or some time, I don't know the time, but so if after some times, if you see that, still they will be there, and you can read it with applying proper VDD, right? Note that if you are applying more voltage, it can damage this, and this state of the value will change. And again, you are programming actually when you are doing that, right? Okay. So now, if you want to go with the retention, it's already known to us that do not apply anything over here. Let it be wherever it's here. So it's floating, right? So you can retain the value, but the problem might be at erase thing, right? If you want to erase it, so there are many ways to erase the value which is trapped here. So one of the ways is, let's apply here negative voltage, very large negative. Like minus 10 volt, 15 volt, something like this. So that these are ground at the time. So 0 volt, 0 volt, and 0 volt. Because of this, these will be attracted. Oh, sorry. These will be attracted, and it will be absorbed in ground, right? So either you go this way, or like there are many ways that you can apply positive itself while erasing. You apply positive, but other side will not be positive, then it will be negative at other side in ground. So you can apply at body side some negative potential or something like that, so that you can erase it accordingly. So let's assume that it's a negative value. If it is a negative value, then what is going to happen? So our band bending diagram was like this. When it was retaining the value, control gate and floating gate, when you are going to give here some negative voltage, so this go up, and so whatever the electrons are there, they can go to the ground side where it is connected to 0 volt, and this one is connected to minus 15 or 10 to 15 volt, something like that, right? So it can erase the data whichever was there. So this was from my understanding and some of the things which I learned from in my previous knowledge. But if we come back to the West and Harris book, you can understand what are the voltages and what exactly it meant to say. So let's start with the program. So this is Weston Harris, where this is a floating gate where body, source, drain all are connected to 0 volt, and you are giving some 20 volt, which is much higher than the supply voltage. In that case, because of the FN tunneling, you can actually program this floating gate with the electron. So you are programming as a 0. Now you can understand when it's 0, when you are going to read this, it will hinder, and there is no current going from source to drain or any other direction. So then you can read 0. But if these things are not there, in absence of that, you can read like there is a direct voltage. But when you are doing this, note that reading purpose, reading 0 or 1, you have to make sure that you are applying VDD at the ground, at gate potential. Otherwise, it will damage the value, right? Okay, so if you don't want to program it, like there is also many ways to do that. So you can look at these combinations and you can understand how these things are happening. And I'm leaving this to you. As I told you, like in other case, I was applying negative potential, right? The example I took. But here, instead of that, body is connected to 0 and this is connected to 0. Sorry, body is connected to 20 and this is connected to 0. So effectively, it's negative, right? So gate to body is negative. So that's how you can erase it. If you want to stop that, do not apply here any potential difference, and there is no flow of charges, right? So these are the combination of voltages, and these numbers are coming from the technology. You need to see what technology you are using. So okay, just revisiting what we were talking about. So this is similar to what you have studied, the NAND flash string, where many transistors will be in series like this. You can see here. We already discussed this, but I'm keeping it for the completeness so that you can understand that what is going on over here. And there will be some two more transistors, which are the normal one. Look at these transistors are the normal one, so that you can read, write, and other things according to your requirement, right? So so this is one of the work which I did with the University of Milan when I was there. So this is one non-volatile flash memory which we develop, and this is one of the popular choice. Note that this is now the thing is, most of the places where you are seeing the the photographs and many other things in iPhone or maybe laptop or other things, the choice of design is NVM flash memory, and it's as good as, it's like you can erase it also. So it's like a double EEPROM, right? And when you're doing this, you can understand now, and if you can relate with the diagram which I showed over there, that when this particular gate is empty, it's a low VT. But when it's filled with electrons, it becomes high VT, and you cannot actually read logic 1, right? It will be logic 0. So VT is going to shift, and this delta VT, so the delta VT is equal to QFG divided by CT. Now you can see that this delta VT is all depending on that equation, where VFG is actually GCR times VG plus QFG divided by CT. You can replace that with delta V if you wish, right? So at the beginning it's 0. So increase or decrease depending on the trapped charges. Okay, so monitoring QT and VTH is required over here if you are designing NVM flash memory. So it's very important that you understand that. And those things are the part of the standard tools like Kane Inspector, Mentor Graphics. I don't know about CMYK, right? So that's why I have not given any task to design NVM flash. Otherwise, you could have done that also, but it's not required. Oh, by the way, yeah, forgot. So as per the trend, there is one more memory which is known as super flash. So here what we have studied, the normal memory will have a floating gate and then the control gate, right? So here what is happening, this guy is actually a bit higher than this one, and always there is a GCR. But instead of that, if you are doing following, something like this, where there is a normal gate, so this will be acting as a control gate, this will be acting as a floating gate, and these will be source and drain. When you are doing this, the best part of this memory is you don't have to go such a high voltage, because earlier what you were doing, you were giving here such a high voltage 15 volt, so that because of GCR you are getting something 9 volt and then it's keep on going down, right? But here in this case, when you want to do such kind of things, you can do with the standard VDD, which is like 1.8 volt or whatever the supply voltage is given, because there is a direct connection is also there, right? And the thing is, you can understand this with the something called CHE. Okay, so something called hot electron injection. This is a phenomena when there is a current from source to drain, and if you apply high gate voltage, what is going to happen? This guy might be like, after applying more voltage, these electrons will try to trap at this floating gate, right? If it is trapped, this is known as channel hot electron injection. Sometimes people call it channel hot carrier injection, because in the case of PMOS and NMOS, for both this is known as carrier injection, right? So this is happening when like you are applying gate potential, and gate potential is like attracting these electrons, and these are being trapped in this floating gate. This phenomena is hot electron injection, as like more number of electrons are going there. That's why like they are considered as hot, because actually there is no terminology with respect to the thermal energy or anything like that, but it's because it's going from this particular channel to the trapped one, which are extra one, and that's why like, and it's acting as programming of the flash memory. That's why it's known as the hot electron. However, there is nothing with respect to its temperature, by the way. So this is called a super flash. Super flash has advantage that you can, you can program it near by VDD voltage itself. You don't need a very high voltage like 15 volt, right? But this structure has to be provided by the technology. So the structure which we have used, it's given by Tower Jazz. It's by Israel, and it was that European Union's project which has been actually executed. So in that, we have used such kind of memory, where it was a sidewall flash memory, where you can see extra two sidewalls are there, and they are acting as a programming medium, right? And accordingly, you can give the source drain potential. Note that while doing this, there are three modes of operation: program, read, and erase, as we know. So if you want to program this, you need to have the channel hot electrons to get attracted. If you want to do that, you can apply very high gate and drain voltage, and maybe source and body to ground, so that you will have a current, and some extra will be attracted over here, and it will be trapped in the this side wall structure. So it depends which side you are taking as a drain or source. Accordingly, things will be programmed. So here you can program it with even with the with the value which is around VDD. You don't need very high value like the case of floating gate we were doing here, because of the side wall flash, which is like a super flash only, right? So because of that, it's also known as super flash. So this structure has direct connection of gate with, this channel. In this super flash which we have projected over here also gate has connection with the channel, right? So that gives liberty to give VDD as programming voltage, right? So same thing is happening over here, that because of this it gives liberty to have supply voltage or the programming voltage as near to VDD, right? So when you are program it, at that time gate and drain both are at high voltage, little bit higher than VDD, let's say. Okay, source and body are at zero potential, and because of that the hot electrons are going into the pinch off region, and the hot electrons have sufficient kinetic energy to cross the potential barrier of the silicon dioxide, and it's trapped in a in a side wall. So when this is happening, it generates the electron hole pairs and impact ionization. All these things, like you might be studying in detail in device course. I am not going into that, and it will deviate the whole purpose of this topic, right? So if that is the case and it's following what you already known, so if there are trap charges, look, it becoming the VT is becoming higher. If there are no trap charges, the VT is the regular one. So there are two plots, IDS versus VGS. This is for low VT and this is for high VT. This is happening when absence of charges in floating gate, and in this case it's a sidewall, right? And this one, it's high in the presence of charges, right? So accordingly it will govern this equation, and that is how, like, this CHE is channel hot electrons, and it uses this spacer. So if you want to read it now, as I told you, the reading part is the one where you are going to give the gate voltage as VDD, and then rest of the places it's zero, and you can ready to read. If the spacer is having the spacer has charges, then you can read memory as a logic 0, and if does not have uh, any charges, you are going to read that one as logic 1. So it's all depending on how you are making the sense amplifier. So program bit at the input of the sense amplifier, it's ready to read, and accordingly you can read all the things. Read mode also act as a standby mode, right? And as I told you, like, this is same equation but taken from different paper. So when you want to erase it, when you are erasing, it's a band-to-band tunneling or the FN tunneling which is happening, and you can have new VTH equation, and it will remove all the charges which were available in the sidewall, or maybe the floating gate, or maybe in the superflash, the structure which is floating, right? So that is what is about this particular topic. I just added because I thought I should teach you something which is new. So that will make the end of NVM. So NVM is the closing chapter right now. Now, just for the completeness, some of the things must be known to you already. But for the completeness, I am following again the Weston-Harris. By the way, if you are interested in the work which I just now talked about, super flash or maybe the sidewall flash, you can read my paper. I don't remember the title, but it's in 2014. workshop on compact modeling. Commonly known as WCL. Okay, so it's the conference paper. If you wish, you can read that, right? So, as I told you, like in the Western Harris, there is another technique which is known as programmable logic array. Notably, the same thing is used to evolve as FPGA, which is field programmable gate array. Here right now it's a logic array. So if you look at all the functions, it has sum of product, right? So if you have sum of product means like this one. So AND gate and OR gate, these two are very important in our case. By the way, title is wrong. It has to be AND OR. Right? So in that case, it's pre-programmed or pre-logic is given here for the case of sum and carry. We know the equation, right? So sum and carry is being made with the combination of different inputs, like you can write down this and you can find out this, right? And for this one, it's AB plus BC plus CA. So if you are interested for this one, you can see AB plus BC plus CA. That will give me the carry out, right? So crux of the story is most of the things are AND or PLA. So in that case, what has been thought that the inputs are given and or lots of things are given together, and you can program them which one you want through such kind of dot diagram, where you know that which one is going to make the connection, which one is not going to make the connection, and accordingly you can read sum and carry, right? So this is one thing. Other than that, you can use the bubble logic over here, which is inverted one, so that like this is for just a standard, right? So when you are doing this, you don't have to use just a plain and or, but it requires actually the NOR and maybe the combination of NOT gate with the or with the another or NOT gate. So such things are already there, and you can again program as I told you for the dot diagram. So if you want to see how it's happening, everything is happening with the fact that you are going to use pseudo NMOS PLA. So pseudo NMOS is the one where the load is like this is the logic and here this is connected to ground, right? So same thing is happen over here for implementing OR plane and implementing AND plane. Both have a load of pseudo NMOS, right? And you can say that this PMOS is grounded. And in AND plane, wherever you are seeing the dot, you're going to add one transistor, and it has to be in series so that it will make the AND operation, right? And because of this NOT, it will become AND, right? Because for these are in series, so that it will make NAND. NAND has to be like it requires one NOT gate so that you can have AND. So that is happening there, and for the OR you are keeping everything in parallel, right? So that you can have the OR operation. So this is how it's actually being made inside this PLA structure. You can add the clock also by adding a clock, right? For phi AND and phi OR. You can add some dummy logic, and if you want to make it dynamic, you can do again with the clocking scheme, right? So various things you can do it, but it's a like same thing. You are trying to make it so that you can achieve lower power. The last one, which is for this all memory cells, one is called radiation hardened. By the way, do you know radiation hardened, Nandit?
Temperature radiation.
Okay, means don't know. So yeah, you are partially correct, but not. So what you are saying, that because of temperature, let's assume that you are making the circuit for harsh environment. So harsh environment covers, automobile or the uh, like circuit which is going to be kept in, let's say, boiler, or let's say it's going to keep near to that IC engine of the car. So in that case, the temperature is pretty high, and in that case, like circuit has to be resistance to the radiation or the temperature things, but that radiation is little bit different. Till it's coming under harsh environment where temperature is pretty high. This is one thing. But other than that, there is something called space application. In space application, what is happening? Let's assume that you are. This is Earth, and you are making your device in a satellite, right? So, and here the circuit is mounted so that it can interact, or it might be, let's say, um, some sort of camera also, just for Google Map or the images from Earth if I want to take. But if you look at this, there is a Jupiter which is very big, and because of that, you might have something called Jovian fields, right? These are pretty high, and while in this one, when it's rotating and things are happening, you might have bombardment of heavy ions like krypton or maybe xenon, ferrum, all this, right? So they might be bombarded over this radiation I'm talking about. Other than that, you might have alpha, beta, gamma, or neutron, right? They are also bombarded on the circuit. Of course, alpha will damage the thing completely. But if other things are there like gamma or beta, and same thing is applicable for the design of some of the biomedical instruments like a PET scanner or the MRI machine, right? Where from everywhere, like this is like circular thing, and here one person is lying where this is going to be operated. Then there are lots of sensors are there, right? And it's also associated with the gamma rays of bombarding, right? So I'm talking about those radiation, and I want to make a circuit which is I would say that radiation resist, or the circuit which is going to be radiation hardened. So radiation hardened might be like a two-way. One is by design, means you are changing the design and such that you can like you can uh, you can withstand such a high radiation. So that technique is called radiation hard by design. And another is also there radiation hard by process. It's RHBP. So, but for that you need to get access of the technology, and where you need to make a big shallow trench isolation, and many techniques are there, but it's a separate topic as we are in design. So we are saying that if I want to make such a radiation hardened SRAM which is going to be sent to the satellite, so if that is there, we need to make sure that that's not going to flip the bit, right? So in that case, its structure is similar, where if you remember in a case of SRAM, we are going to have such structure, right? But instead of that, instead of two inverters, we are adding two more inverters. Instead of two inverters, two more are added, and there both the gates are not tied together. Means NMOS and PMOS. Maybe I'm keeping this to you people how it's working. You have to feed 1 and 0 so that you can understand it's not going to damage at all. Or even if there is something is happening, it's going to be restored as we want, right? So let's concluding the chapter with the different DRAM generations. That so different innovations happen and different time is happened. So you can see that from 1970 to 2010 different memories came, and even like some double data rate interface memories like DDR also came into picture after like 2001, right? So this topic does not stop here. It's just a starting of what memory is. So these are just introduction of how memory works, right? But if you want to go further for more understanding, and believe me, it has lots of potential for getting job, doing research, and of course it's very interesting also. And it's that's the memory is the block which is taking the highest area of entire chip. So you have to feed lots of attention on that, and there are many people who work on these things. So it might be useful for your further career also. If you want to take this one, you can